Live. A very warm welcome to all the participants. I, Dr. G. Haripriya, HOD of H&S Department and convener of 1 week international online FDP entitled Mathematics for a Better World. It's my privilege to introduce our resource person of today's session on graph theory and applications, Dr. Srinivasacharya, Professor of Mathematics, NIT Warangal. Sir is currently handling the courses Symbolic Computing, Discrete Mathematics for MSc. Sir has also taught for undergraduates. He guided 46 MSc projects and 16 PhD students. He organized and attended national and international workshops, conferences, STTP projects in the field of mathematics. Sir has been honored with Best Science Researcher Award. Sir also the member of Executive Council of ISTA. A life member of Andhra Pradesh Society for Mathematical Sciences, India Society of Theoretical and Applied Mechanics. Sir has additional responsibilities like Head of the Mathematics Department, Chief Warden, In Charge, Computational Lab, President of Teachers Welfare Association of National Institute of Technology, Warangal, Associate Dean, Faculty Advisor for MSc, General Secretary of Teachers Welfare Association of National Institute of Technology, World Congress on Engineering and Technology, China. Sir, we are very fortunate to have you for today's session and I request you to address the participants. Sir, please take over the session, sir.
Thank you very much for introducing me. Can we start the topic now?
Yes, sir.
Okay. So this is a topic which I am going to give lecture. That is graph theory and applications. Okay, before going to the details, just let me explain you how these graphs are used in our daily life, how graphs are used in our daily life. Many of you are students and faculty, maybe teaching course. So if you take a chemistry faculty, it draws a graph, it draws a lines, relations, it draws relations among atoms and molecules. Take organic chemistry, they draw a graph, a structure like this, which we call as, I don't know exactly. So this, I drew in components here. So like this, he sketches the relation between all atoms and molecules. Similarly, an engineer draws a schematic diagram of electric bulbs. If you take your residence, if you want to go for wiring, electric wire in your residence, then he draws a sketch how the wire should be, or where the tube is to be fixed, where the fan is to be fixed, where the switches are to be fixed. All these things he'll put a diagram. Similarly, a genealogist draws a family tree. Family tree, you may go to your family tree, father, children, and then again children to this child, like this. A family tree can be drawn, right? A socialist maps the power structure of large corporation. If you take a corporation like your institute, chairman, then secretary, correspondence, again like this, all power structure. What is the structure of the different administrative positions in your organization? So that shows a map. In each one of these 4 examples, a set of points here. This is one point, this another 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 point. A set of points are connected. Here also, this is one hierarchy. Hierarchy of the family, second level hierarchy, third level hierarchy, like this. We have some points, and these points are connected. So each one of these we call as a graph, connected some lines. Each one of these is called a graph. So graph is nothing but points connected by some lines. Take some points, connect them by some points, then we call it as a graph. So some points here like this, and try to connect them by means of the lines. So this we call it as a graph. How this graph is used? So this is an example for a graph. If you go to your computer lab, all the computers are connected through networking. All the computers are connected through networking. So this is also an example where the computers are the points and the wiring connecting the computers or the lines. All the computers take them as points, and the cables which connects the computers that we call as lines. So this networking is also graph. Similarly, you can treat the society as a graph. For example, take the people as nodes. Different people in the society, take them as nodes like this. Different people in the society, take them as a nodes, and then relationships. These relationships can be either family members or friends or co-workers or followers or authors, like this, anything. Relationship represents the edges. So if one person is neighbor to other person, we draw a edge between these two. If this person is neighbor to another person, we draw an edge from this person to this person. Here all the people are denoted by nodes, all the people denoted by nodes. Suppose if this person is colleague in an office, then we draw a line here. If this person is a friend to this person, then we draw a line here. If this person is traveling in the same bus to the office, then we draw a line here. So like this, all relationships, we denote them, we draw a line for the relationship, and we try to connect the people. Therefore, the total society can be treated as a graph. Total society can be treated as a graph. So relationships may be acquaintanceship, friendship, co-authorships, colleagues, anything. Anything can take as a relationship, and then try to connect the people through an edges. The example, whatever I told here. So the dots, the points which are in yellow color are the people, and the lines are the relationships. As I told, the relationships can be either lines, relationships can be either acquaintanceship. If a person is neighbor to other person, then we draw an edge between those two people. Similarly, if a person is a colleague to other person, then we draw an edge, then we draw a line between those two persons. Like this, if you take the relationship as an edge and people as the points, then you can draw a graph for the society. So this is what I told. The network, computer networks, looks like a graph, which I told in the beginning. All the computers are nodes, and the cables connecting the computers are the edges. Therefore, this is another example for a graph. So like this, you will have several examples in your daily life for the graphs. There are several examples for the graph in your daily life. So graph models, where these graphs, some more examples of the graph models. First, we take what is graph and what is the vertices. Suppose if I represent a model as a graph, then I have to identify what are the vertices, what are the edges, and what data is transferring. That I should try to explain through examples. So suppose if I take communications, suppose if I want to call you by phone, then my mobile phone is one node and other mobile phone is another node. And so therefore we can take the telephone exchanges or computers or satellites as nodes. In case of, if you treat communications as a network, if you treat communications as a graph, then the nodes are nothing but telephone exchanges, computers, satellites, like that. We can give any number of things. Now, how these telephone exchanges are connected? Through cables. How these computers are connected? Through cables or fiber optics or microwave relays. Like this, these telephone exchanges or computers or satellites are connected. Therefore, in this case, the edges are nothing but cables, fiber optics, microwave relays, etc. In this case, what is transferred? A data is transferred from one node to another node. Therefore, the flow is here, voice. The flow is here. When I talk here, you are able to listen. Or you are able to listen while I am talking in my home. That is through microwave relays. So microwave relays, you are able to hear my lecture by sitting at your home. I am sitting in my home, but you are able to hear my voice. Here, my system is a node. Your system or your mobile is another node, and these two are connected through the cable or fiber optics. These are connected through the fiber optics, and then the voice. Whatever I'm talking here, you're able to hear. Whatever I'm talking here, you're able to hear. Therefore, the voice is transferred. Therefore, the flow is here, voice from my place to or my computer to your computer. So sometimes you can also transfer videos. If I start my video, then you are able to see me also. Okay. So therefore, here, in case of if you treat communications as a graph, then the vertices are telephone exchanges, computers, satellites, and the edges are cables, fiber optics, microwaves, and the data that is transferred. The flow is either you can transfer the voice from here to there, or you can transfer the videos, or you can transfer the packets. In case of networking, you are able to transfer the packets. Therefore, this is one example. This is one example for the graph. Another example is circuits. Circuits, you know what is circuit. Okay. If you treat circuit as a graph, then the nodes are gates, registers, processors. If you take your computer, motherboard, what you call it as a motherboard, different parts are connected through wires. Different parts are connected through wires. Here the parts are processors. Different processors or microchips or something else is connected through wires. Therefore, here the edges are nothing but wires. And what is flowing in circuits? Current is flowing from one place to another place. If you take your electric wiring in your home, then that can be treated as a graph where the switches are the whites are the edges and the switches are the nodes. Then switches are holders, whatever you want to be, fans or tubes, whatever we get, they will call it as nodes. And here, this case, what is transferred? Current is transferred from one vertex to another vertex through the edge. Edge is here, wire. To an edge, the edge is nothing but wire here. In case of mechanical, the applications of graphs in mechanical engineering is joints. And then rods. We join two things by rods, beams, springs. So joints are the vertices. Different joints are joined with either rods or beams or springs. So this is, you can take it as a application of the graph where the vertices are joints, edges are rods, beams, springs, etc. And what is transferred? You can transfer a heat or an energy from one joint to another joint. From one joint to another joint, you can transfer. You can take your vehicle. Your vehicle, all the wheels are connected through rods or springs, like that. So if you take all the wheels as vertices, then all these wheels are connected through rods. Again, this total completely connected to your steering, and steering is connected to gearbox like this. Different parts in a car are connected through rods, beams, and springs. Therefore, we can take this as a graph, example for a graph. In case of hydraulics, in case of hydraulic graph or hydraulic network is you have some water tank, overhead tank in your house, and from overhead tank, the water is distributed to different places in your house. Okay, so how this water is distributed to different places? Maybe a tap in the kitchen, a tap in the bathroom, or a tap outside the wash area. Like that, you have different types. So here, the different types are pumping stations. That we have take specific example of house, but this is general examples. Different reservoirs and then pumping stations. So you get the water supply to your home from a different pumping station. In a city, municipality will supply the water to each and every house. How they are supplying? Water will be stored in the reservoir. From the reservoir through pipelines, the water will be distributed to different houses. So here, the reservoirs and pumping stations, so you can take them as vertices, and these are connected to the pipelines. And in this case, what is transferring? Either you can transfer a water, that is fluid, or you can transfer oil. The oil, either oil or fluid or water, something will be transferred from one vertex to another vertex. So this is another example for a graph model. Another graph model is financial. So in this financial, stocks and currency, we can take them as nodes, and edges are transactions. So what is transaction here? Money. Money is transferred from one place to another place. So if I want to transfer the amount from by sitting here to your account, then you have to open your system, and then you have to transfer the transaction. Some transaction you have to do through a bank. So therefore here transaction is the edge, and stocks currency is a vertex, and what is transferred here? Money is transferred from one vertex to another vertex. So this is another example for a graph model. And then in transportation, the graphs can be modeled by taking airports, rail yards, street intersections, bus stations, railway stations. All these things you can take as vertices. So different railway stations are connected through highways, or railway stations are connected to rail beds, and different cities are connected through highways, and different airports are connected through airway routes. Therefore, here, if you take airport as a vertex, and different airports are connected by airway routes, so they can take different airports as the edges. Okay, different airports as the vertices, and the airway from one airport to another airport, you can take it as an edge. Similarly, different railway stations as vertices, and trains or railway tracks connected from one railway station to another railway station, you can take them as edges. And what is transferred here from vertex to vertex through edge, the transfer is here at flights or vehicles or passengers. These things are transferred from one airport to another airport, or from one railway station to another railway station, like that. So these are different graph models that we use in our daily life. These are the different applications of the graphs in daily life. Before going to detailed applications of this graph theory, just I'll introduce mathematically what is a graph and how these graphs are defined, what are different types of graphs, some basic definitions. Maybe you may be familiar with these basic definitions, but still, just I would like to give a brief introduction, definition, and some properties of the graphs. So for each property, suppose if I say that Eilerian graph, so what is the application of Eilerian graph? Suppose if I take Hamiltonian graph, what is the specific application of the Hamiltonian graph? What is planar graph? What is the application of the planar graph? Like that, I should try to give a detailed explanation for the applications of different types of graphs. So before going to the details, just I would like to give you the basic definitions of the graph. Simple definition is, in whatever I told, there are examples, real life examples of the graphs. But here, mathematically, when a graph as the set of the ordered pair of two sets, V comma E, we define the graph as V comma E, where V is the set of vertices. As I told in the previous examples, if I take different railway stations as vertices, and the connecting railway stations connected through railway tracks, you can take them as edges. So vertices is one set, E is nothing but set of vertices, and E is a set of edges. Then the set of vertices together with the set of edges, that we call as a single graph. That is, these two are connected through an unordered pair. These two are connected through an element from the vertices, and a vertex is connected to another vertex through an edge. Therefore, here B is the set of vertices, E is the set of edges. So this E contains unordered pairs. The elements of E contains unordered pairs. This is the mathematical definition in which you have an idea about what is meant by graph, how these graphs are applied in our real life. So, for example, if E is an edge, then E is an unordered pair. U comma B are the vertices of. If U comma B are the vertices, suppose this is one vertex U, this is another vertex B. Now we join these two vertices by an edge. So joining these two vertices by an edge is denoted by this unordered pair. Joining these two vertices by an edge is denoted by an unordered pair U comma B. So undirected graph means that undirected graph may contain loops, Suppose if I take this may contain a loop. Loop means if there is an edge from a vertex to itself. Suppose this is a vertex U. If you draw an edge from vertex to itself, then we call it as an edge. Therefore, a simple graph, not simple, a graph may contain loops. What is a loop? Loop is nothing but an edge from a vertex to itself. Suppose if this is a vertex, if you draw an edge from vertex to itself, then we call it as a loop. Another one is, this is about simple graph. And we have another type of graph where it is called as directed graph. If you take the current flow from one switch to another, from switch to light, the current flow will be in only one direction, not in the reverse direction, right? So therefore, you can treat that as a directed graph. A directed graph contains, again, same thing, set of vertices and a set of edges. But here, E, the set of edges is nothing but ordered pairs. In case of simple graph, the edges are unordered pairs. In case of directed graph, the elements are ordered pairs. That's the only difference between the simple graph and directed graph. So if E belongs to E, same definition. Here this is a notation of unordered pair, and this is a notation of ordered pair. This is a notation of unordered pair, this is a notation of ordered pair. You find only this difference between the simple graph and directed graph. Just I'll give you one more example for this simple graph. Same thing, loop, whatever the loop defined for simple graph, same definition holds good for directed graph also. A simple graph is just like a directed graph, but no specific direction. The difference between these two, as I told, directed graph means a graph which has directions. Directions, upward direction, downward direction, rightward direction, leftward direction, some direction. The each edge should have some direction in case of directed graph. In case of simple graphs, no directions. The flow can be either way, from one vertex to another vertex in any way. There is no restriction. So an example for graph model is, how can you represent a network of railway connecting a set of cities? Railway is connecting a set of cities. This is bidirectional. One, for example, if I take this, we should use a simple graph with an edge A, B, indicating a direct train which connects between the cities A and B. If there is a direct train which connects the cities B and B, then we can take A and B as an edge. So it connects two stations A and B, means a train can go from A to B, or a train can go from B to E also, both the directions. There is no specific direction. So for example, if I take these, Nagpur, Warangal, these are the different two different examples anyway. Nagpur, Hyderabad, Warangal, Vijayawada, these are the different cities. These cities are connected through lines. If there is a train between Nagpur to Warangal, then we draw an edge. If there is a train from Nagpur to Warangal, the train may go from Nagpur to Warangal, or the train may go from Warangal to Nagpur. So then we draw an edge between Nagpur and Warangal that indicates that these two cities are connected by a train. These two cities are connected by a train. Similarly, if there is a train from Hyderabad to Warangal, then we draw an edge. If there is a train from Hyderabad to Warangal, that means Hyderabad and Warangal both are connected, and we try to draw an edge from Warangal to Hyderabad, taking them as vertices. And similarly, if there is a train connection between Warangal to Vijayawada, then we join them by edge. So this is the example for simple graph. Similarly, there is no train from Hyderabad to Mumbai, that's why they are not connected. There is no train from Warangal to Rourkela, that's why they are not connected. But there is a train from Rourkela to Mumbai, therefore they are connected. This total, you can assume it as a simple graph. You can treat this total as a simple graph. Similarly, I shall try to give one more example for directed graph. So directed graph, if you take the round robin tournament, suppose if there are 5 players, then 5 teams, not players. But in case of single player game, there can be 5 players. If there are some teams, then each team has to play against other team exactly once. That means if I take the team A should play with team B, team C, team D exactly once. Similarly, team B should play with team A, team C, team D exactly once. So therefore, this can be represented in the form of a graph. So here, the edge is nothing but if the team A beats the team B, then we say that there is an edge between A and B. Then we draw an edge between A and B, and we represent this round robin tournament as a graph. So we should use a directed graph with an edge A, B, indicating that the team A beats the team B. That is, the team A defeats the team B. If the team A defeats the team B, then we draw an edge from A to B, the direction from A to B. So this is a team A, team B, team C, team D. Suppose team A beats team B. Right? Team A beats team C. That means team A defeats team C. Then we draw an edge from A to C. The meaning of this is team A defeated team C. Similarly, team B defeated team A. So there is an edge from B to A. Because team B defeats team A, then we draw an edge from B to A. Similarly, team B defeats team C. Therefore, we draw an edge from B to C. Team B defeats team C. Therefore, an edge from B to C. Then team D defeats team A. Therefore, an edge from D to A. Like this, we draw the edges. So this is an example for directed graph. So in this case, team A is playing with team B, team B, team C. Team A is playing with team C, team B, team D. But the case is, team A is defeated by team B, team A defeats team C, and team A is defeated by team B. Similarly, if I take team B is also playing with the remaining three teams exactly once. And in this case, we represent the graph in the form of a director. We represent this totally in the form of a director graph that we call as tournament graph. Anyway, I'll tell you the details of these. What is the ranking, tournament ranking, that I'll try to explain in detail once we complete the basics of these graphs. Okay, so this is an example, another example for a graph, a directed graph. The previous one is example for simple graph. This one is the example for directed graph. Then two vertices. This again a definition. Two vertices U and V in an undirected graph are called adjacent if there is an edge from V to V. Suppose if I draw this graph, suppose if I take this graph, and this is edge A, U, this is edge B. Suppose, sorry, this is our vertex U, this is our vertex V. Suppose if there is an edge between U and V, then we see that U and V are adjacent to each other. Then we say that U is adjacent to V and U and V are called adjacent to each other. If there is an edge from U to V, similarly, if I take this as W, U and W are adjacent, V and W are adjacent because there is an edge between U and V. Sorry, V and W, there is an edge between U and W. Therefore, we can say that U, V are adjacent, U, W are adjacent. Similarly, if there is an edge, E is equal to U comma B, the meaning of this is there is an edge from we are calling that edge as E from U to V. That is, there is an edge from U to V, and we are calling this edge as E. So this is the meaning of E is equal to U comma V. So E is equal to U comma V. The edge is called incident with the vertex U and V. That means it is ending. It is incidenting on the edge U and also on the edge V. Therefore, we say that this edge is called incident with the vertices U and V. The edge is also said to connect U and V. Two vertices U and V are called endpoints of the edge. Suppose if I draw this edge between U and V, so this U is endpoint to this edge, one endpoint to this edge, and this one is another endpoint to this edge. Therefore, this U and V are called endpoints of the edge U comma V. And degree, number of edges incidenting on a particular vertex, except that loop. The loop is counted twice. Okay. So if you count number of it, you know what is meant by incidenting. Incidenting, the edges which are reaching a particular vertex. The edges which are reaching a particular vertex. Suppose this is one edge, this is one edge, this is one edge. These are three edges incidenting on the vertex V. So these number of edges we call it as degree of the vertex. Similarly, if I take this as a vertex and this another vertex, now for this vertex, two edges are incidenting, therefore degree of this vertex is 2. So like this, the degree of the vertex is defined. Number of edges incidenting on a particular edge, we call it as degree of the vertex. and it is denoted by deg of v. And suppose if there is no edge, simply by take only this vertex. So how many edges are incidenting on this? There are no edges. So this we call it as isolated vertex. So if the degree of the vertex is 0, that means if there are no edges incidenting on a particular vertex, then we call it as isolated vertex. So a vertex with loop has at least degree 2, because if you take this loop, so this is one vertex adjacent, this is one edge incidenting on this, and again the end of this edge is also incidenting on this. Therefore, if you take a loop, the degree of the loop is 2, and by definition, this is not isolated. Even it is not isolated, it is not incidenting on any other vertex, even though it is incidenting on itself. Therefore, it is not isolated. So, degree of a vertex of degree 1 is called pendant. Suppose if I take this and only one edge incidenting on this, then we call it as pendant. It is adjacent to exactly one vertex. Okay. Example. So these are different. This is a graph where the vertices are A, B, C, D, E, F, G, H, I. A, B, C, D, E, F, G, H. There is no I. A, B, C, D, E, F, G. So these are different vertices, and edges are given. Vertices are given in red color, and edges are given in green color. Now try to find the degree of each vertex, or try to identify are there any pendant edges, vertices, or the independent vertices, any isolated vertices, or how many loops are there, how many isolated vertices, how many loops, how many pendant vertices. Like this, we can calculate from this graph. So here A, only one edge is incidenting on A. Similarly, only one edge is incidenting on D, and only one edge is incidenting on J. If I take A, D, A, D, and J, suppose if I take these three, only one edge is incidenting on A, only one edge is incidenting on D, only one edge is incidenting on J. Therefore, we call them as pendant. So A, D, J are pendant vertices. And similarly, E has a loop, G has a loop. And how many vertices incidenting on B? There are two vertices which are incidenting on P. Therefore, degree of B is 2. And there is no vertex incidenting on F. There is no edge incidenting on the vertex F. Therefore, this vertex F is isolated vertex, because there is this GHI. So typing mistake, this is I maybe. Typing mistake F, GH, IJ, right? This is I, not F, both of it. Now here this is isolated vertex, because there is no edge incidenting on this. So that's what it is written. The vertex F is isolated, and vertices A, D, J are pendant. And maximum degree, but only this has, because it is a loop, we are counting it as 5, 2, 3, 4, 5. So maximum degrees, G has a maximum degree, which is nothing but 5. Degree of this is 2, degree of this is 1, degree of this is 1, degree of this is 2, 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 degree of this is 5, and degree of this is 1, and degree of this is 0. Just count the number of edges incidenting on a particular vertex, and then you decide the degree. Okay. So here maximum degree, G has a maximum degree, and it is 5. The maximum degree is G. Maximum degree is 5, which is has the vertex G. The graph is pseudo graph, that is, it is not directed, but it has loops. All types of vertices exists in this graph. So that's why we call it as pseudo graph. Then, this is a well standard theorem in graph theory. That is, if G is equal to a graph from the set of vertices V to the set of edges E, then twice the number of edges is equal to sum of the degrees. So sum of the degrees of the vertices is equal to twice the number of edges. Sum of the degrees of vertices is equal to twice the number of edges. This we call as handshaking theory. You know what is meant by handshaking, right? If 20 people handshakes with each other, the number of handshakings is nothing but twice the number of hands. So like that, you can write this as handshaking. Another one is this is U is said to be adjacent to V and V is said to be adjacent from U. Same thing, whatever the definition I have given earlier. And here the initial vertex of U comma V is V. U is the initial vertex. This is the terminal vertex. In the edge U comma V, U is called initial vertex, V is called terminal vertex. So if the initial and terminal vertices of the loop. So for this loop, initial vertex is same, terminal vertex is same. Therefore, the initial vertex and terminal vertex of the loops are same. This is in degree. This is in case of directed graphs. Previously, I defined degree for undirected graph. Now the definition of degree for directed graph. In this case, you have two types of degrees. One is in degree, another one is out degree. In degree means the number of edges incidenting on a particular vertex. Out degree means the number of vertices leaving from a particular vertex. The number of vertices joining a particular vertex. In degree, the number of edges joining a particular vertex. In degree, number of vertices leaving a particular vertex that we call as out degree. So the out degree is nothing but number of edges with V as an initial vertex, and it is denoted by G plus. And out in degree, number of vertices with V as a terminal vertex. So in degree means dV, out degrees, degrees joining, out degrees leaving. Suppose if I take this directed graph, then again example here, this is a directed graph. In this directed graph, so what is the degree of A? In degree of A, 1. So because only 1 degree, only 1 is coming to this vertex, that is this vertex, AC vertex. So AC edge is coming to you. Therefore, in degree is 1 and out degree is 2 because two vertices, two edges are leaving from A. Two edges are leaving from A, so out degree is A. Only one vertex. This vertex is joining A, therefore in degree is 1. Similarly, for this 1, 2, 3, because it is a loop, we count it as twice. So 1, 2, 3. So out degree 1, 2, 3, 4. So in degrees joining 4 and out degrees 2, leaving the vertex. Only 2 vertices are leaving the vertex. 2 edges are leaving the vertex. Similarly, no vertex joining the no edge joining the vertex C. In degree is 0. No vertex. So two edges are leaving C. Therefore, out degree is 2. So like this, you can find in degree and out degree. And we'll go to the special graph, some special type of graphs. Then a simple application of this special type of graphs. A complete graph with n vertices denoted by Kn is a graph that contains exactly one edge between pair of distinct vertices. If you take any pair of vertices, then there should be only one edge. Then we call it as complete graph. So you complete graph with one vertex. You simply align K1, that is denoted by K1. A complete graph with two vertices will be denoted by K2. There are only two vertices, and there should be exactly one edge. That edge is here. Suppose if I take 3, so between these two, exactly one vertex edge. Between these two, exactly one edge. Between these two, exactly one edge. If you take any pair of vertices, there is only one edge. So this is K3. Complete graph with 3 vertices. This is complete graph with 4 vertices. And this is complete graph with 5 vertices. This is complete graph with 5 vertices. Complete graph, if you take any, suppose if I take any pair of vertices, there must be only one vertex. Sorry, only one edge. Therefore, we call that as complete graph. A cycle consists of the starting point and end point of the complete graph must be same. The starting point and end point of the complete graph must be same. So this is a cycle. This is a cycle. C3, cycle 3 vertices, cycle with 4 vertices. That is V1 to V2, V2 to V3 should be an edge from V1 to V2, V2 to V3, V3 to V4, V4 to V4, etc. Again, Vn to Vn, Vn to V1. Then we say that is a complete cyclic graph. This is cyclic graph. This is another example of cyclic graph. And this is another example of a cyclic graph. So all these are examples for cyclic graphs, right? It forms a cycle. The starting point and ending point are same. And then wheel graph means there should be a center and all the vertices should be connected to the center. That we call as a wheel graph. So here the center is here. So all the vertices connected to the center. Therefore, complete graph The wheel graph is a complete graph where there is one vertex which is called Cartridge center and which is connected to all the remaining vertices. So here this is a wheel graph. So this is center. First of all, it is a complete graph, and there is a designate a vertex as a center such that this vertex is connected to the remaining vertices. So that we can as wheel graph. This is another example for a wheel graph with 5 vertices. Wheel graph with 6 vertices. 1, 2, 3, 4, 5, 6. Wheel graph with 6 vertices. That is denoted by W6. And complete bipartite graph. You know what is complete graph? Bipartite means divide the vertices into 2 sets, M comma M. Divide the vertices into 2 sets such that each vertex in M is connected with each vertex in M. Each vertex in M is connected with each vertex in N. But vertices within M are not connected. Vertices within N are not connected. So divide the total vertices into 2 groups such that there is an edge from vertex of the first group to vertex of the second group, but there is no vertices within the group. So example, if I take 3, 2, so we are dividing total 1, 2, 3, 4, 5 into 2 sets, 3 and 2, such that each vertex in this is a vertex, this is connected to the remaining 2, this also connected to the remaining 2, this also connected to the remaining 2. So this we call as complete bipartite graph. Bipartite graph, if you are able to divide into, if you are able to partition into 2 groups, such that one vertex in the first group is connected with one vertex in the second group. And if every vertex is connected with every vertex in first group is connected with every vertex in the second group, then we call it as complete bipartite. Bipartite simply take 2 groups and one vertex in this group should be connected to one vertex in this group. That is bipartite. Complete, all the vertices of this group should be connected with all the vertices of this group by means of only one edge. Then that is called complete bipartite. So this is one example. K3, 4, we divide into 3 vertices and 4 vertices, and then we try to connect it. This is K3, 4. So another practical application of this matching, we can use this bipartite graph for matching. That we call as stable marriage problem. Another version of this problem is false marriage problem. So here we divide men and women as 2 groups. We divide total into 2 groups. One is men, another one is women. So look at young men and young women with the partner preferences. So these men have some preferences for their partners. These women have some preferences for their partners. Now we try to denote this one by a complete. We try to do this as a bipartite graph, and we try to match. We try to find the matching between men and women with their partner preferences. So this application of the bipartite graphs. This is one application of the bipartite graph that we call as in the literature. It is called as stable marriage problem. So for any pair, Alice and Bob, one of the following conditions is true. First one is Alice and Bob are married. That is either this is true, or Alice prefers her partner to Bob, or Bob prefers his partner to Alice. So if you take any pair means one from men, another from women. Take any pair, one from the set of young men, another from the set of young women, and then this pair should satisfy one of these 3 conditions. If you take anyone from this, then this person group you have taken from this maybe marry the woman in this group, or this person from this group may prefer a woman in this group, or a woman in this group may prefer the men in this group. One woman in this group may prefer one man in this group. So therefore, if you take a pair, one from this group, men's group, another from women's group, then the relation between these 2, that is, the relation between those 2 is the thing that either they are married, or a man which you have taken prefers a woman, or a woman which you have taken prefers a man. One of these 3 conditions are true. Now, this condition is not true. That means if you take A, B, C, D, such that AD and BC would both be preferred, means A prefers B, A prefers D is not preference. It is not a correct preference. A can prefer only B, but A cannot prefer D. Similarly, C can prefer only D, but C cannot prefer B. That's why only these three conditions are satisfied. Either one prefers.
Madam,
only
YouTube
one.
plus one.
Yes. Any problem? Hello. Any problem?
Continue, sir. No problem, sir.
Okay. So if I take the pair A comma B and C comma D, so A cannot prefer D, A can prefer only B, but A cannot prefer one more person. Similarly, C can prefer only D, but C cannot prefer B. So B can prefer A, but B cannot prefer C. So this condition could both be preferred such that no pair. So you cannot find such pairs. Okay. Now, what is stable marriage problem? In this case, with the conditions which were given in the previous slide, that is, if you take a person, a man, and a woman from two different groups, then there are three conditions. A man which you have selected and a woman which you have selected, both are married. That is first condition. Or a man from the first group may prefer a woman in the second group, or a woman in the second group may prefer a man in the first group. A man in the first group may not prefer two women in the second group. A woman in the second group may not prefer two men in the first group. So these are the conditions which are given in the previous slide. Under these conditions, stable marriage always exists for any preference. Whatever is the preference between men and women, a stable marriage always exists. So this we call as stable marriage problem. So this girl-oriented algorithm, there is a stable marriage problem algorithm with girl-oriented. Just I'll give the list. Girls successfully make proposal to boys, engaged or not. That means get men and women. I mean, it is shifted to girls and boys. Okay. So girls successfully make proposal to boys. This is girls-oriented algorithm. But then you can similarly take the boys-oriented algorithm also. And then if a girl proposes to a boy who is free, not yet paid, take a boy. If girls takes a boy from the group, boy who is not engaged, who is free, that is, he is not yet paired with the other girl, then the boy accepts the proposal. If the girl proposes to a boy who is free, not paid.
Sir, sorry for the disturbance, sir.
Yeah, tell me.
Sir, 2 minutes, sir. Sir, a live YouTube live పోవట్లేదు sir. 2 minutes, sir.
Okay, is it fine?
Wait, sir. 2 minutes, sir. Due to some network issues, sir.
Okay.
Sir, continue for this session, sir. Sir? Sir, excuse me, sir.
Yeah, tell me.
Sir, please put on your video, sir.
It is already on. Sharing online. Screen sharing on.
Screen share on, sir, but your video also on, sir.
You want video also?
Yes, sir.
It's coming. Is the video coming?
No, sir.
I switch on my video.
Okay, sir.
It's coming now.
Yes, sir. But your face is not visible, sir. Video is on, but your face is not visible, sir.
Yeah, that's what I'm also unable to see.
Yes, sir. Okay, sir. Continue this session, sir. Okay, sir. Continue this session, sir.
Okay. Wait. Right. So this is second step. Third one is if the girl proposes to a boy who is already paired, then there are again two cases. If the proposal is better proposal from the boy's perspective, then the boy breaks the whole proposal and accepts. So this is the first case is if the girl proposes to a boy who is free, then the boy accepts the proposal. There's no issue in that. Second case is if the girl proposes to a boy who is already paired, then the boy will think whether it is better proposal or the old one is better. If the new one is better, then he breaks the old one and accepts the new one. If the new proposal is not better, then the boy rejects the proposal and keeps the old proposal as it is. Therefore, the key for the proof of this is consider arbitrary curl G. If G prefers B dash to B, that is already G has preferred B, but G prefers B dash, then B dash must have rejected G and been paired with some G dash, whom he prefers to G. As the choice of G is arbitrary, there are no unstable pairs. All the pairs are stable. So this we call it as totally it requires n square iterations, and this is curl optimum. The solution which we are getting by the proof given here. This is we call it as optimal curl optimal solution. So this we call it as stable marriage problem. Another version of this is false marriage problem. It's another version of the same problem. A class contains some girls and boys. Each girl likes some boys and does not like others. This is the first condition. Under what conditions can each girl be paired up with a boy that she likes? If you take a class, there are some boys and girls. Each girl likes some boys, not only one, more than one, and does not like others. Under what conditions can each girl be paired up with a boy that she likes? So this can be solved by using bipartite graphs, partition graphs. This can be solved by matching technique of the. We can model the situation by a bipartite graph. So create a vertex on the left of each girl. Here I have taken on the top of each girl. First row we take all the girls and all the vertices in the first row for girls, all the vertices for the second row for boys. If a girl likes a boy, put an edge between them. For example, we take this example. So Alice likes Chuck, therefore there edge from Alice to Chuck. Alice likes John, therefore there edge from Alice to John. So Martha likes Michael, therefore there edge from Martha to Michael. Martha likes Kim, therefore there edge from Martha to Kim. Similarly, Sarah likes Chuck, therefore there edge from Sarah to Chuck. So Sarah likes John, therefore there edge from Sarah to John. Similarly, Jane, there edge Jane likes Tom, Jane likes Michael, Jane likes Keith. Therefore, there are 3 edges from Jane to Michael. So like this, we represent here 1, 2, 3. There are 4 girls: Alice, Martha, Sarah, and Jane. And there are 5 boys: Chuck, Tom, Michael, John, and Keith. So some of these girls likes some of the boys. So each girl means Alice likes 2 boys, Chuck and John. Martha likes 2 boys, Michael and Keith. Sarah likes 2 boys, Chuck and John. Jane likes 3 boys, Tom, Michael, and Keith. Therefore, this can be represented in the form of a bipartite graph, where one partition denotes the girls, another partition denotes the boys, and the edges between these 2 partitions are nothing but whether a girl likes a boy or not. Okay, now in graph terms, our goal is to find matching. What we have to find in the previous case, under what conditions can each girl pair up a boy? That means you have to find a matching for boy, for a girl in girls group to a boy in the boys group. You have to find a matching. This is nothing but matching problem. This can be solved by using the graph theory. The subset of edges such that exactly 1 edge is incident on each girl, and at most 1 edge is incident on 1 boy, each boy. So now we have to find, our goal is to find matching such that exactly 1, we have to find a subset of edges such that exactly 1 edge incident from each girl, and at most 1 edge incident to a boy. For example, here is one possible matching for the girls. So here we have the girl, the edges in pink color, or the matching. The edges in pink color matching. So here, Alice, there is a matching between Alice and John, Martha and Michael, Sarah and Chuck, Jane and Keith. So there is a matching. So our aim is to find such a matching. For this, we use the theorem that we call it as false marriage theorem. So which states that necessary and sufficient condition for the existence of a matching in a bipartite graph. So this false marriage theorem states the matching between matching in a bipartite graph. So this is the example which is available in the literature, which is explained to find the matching in a bipartite graph. A simple example. This is another application of the. So here we state and prove false theorem using girl likes boy terminology. Define the set of boys like a given set of girls to consist of all boys liked by at least one of those girls. So these are the, for example, if you say set of boys liked by Martha, take the previous one. So set of boys liked by Martha is 1, 2, Michael and Keith. Martha and Jane both consist of Tom, Michael, and Keith. So for us to have any chance at all of matching up the following marriage conditions, so the marriage condition is every subset of girls likes at least as large as a set of boys. Every subset of girls likes at least as large a set of boys. So we can not find a matching for some 4 girls likes only 3 boys. You cannot find a matching for 4 girls likes 3 boys. If 4 girls likes 4 boys, then you can find a matching. Otherwise, you cannot find a matching. So Hall's theorem states that a matching for a set of girls G with a set of boys B can be found if and only if the marriage condition holds. The marriage condition is here. The marriage condition is given here. It's a marriage condition. If this marriage condition holds, then you can find a matching for a set of girls with a set of boys. So this we call it as Hall's theorem. Anyway, I'm not giving the proof of this theorem. You can find this proof in the literature. So another one is Paulson circuits. Yes, I'll take a first. These are definitions of the Paulson circuits. Path means an edge, a sequence of edges from one vertex to another vertex, such that the end point of one vertex is the starting point of the other vertex. That we call it as a path. Circuit, in a path, if endpoints are same, then we call it as a circuit. A path or circuit is simple if it does not contain same edge more than once. So connectivity, if you take any 2 vertices in a graph, if there is a path between 2 vertices, every pair of distinct vertices, then we call that the graph is connected. Any 2 components in network and can communicate if and only if the graph of this network is communicated. Suppose we are in the network, all the participants and speaker and a host. All of us are in a network. So I can communicate to the participants only if there's a path. The path is whatever the lecture I'm giving, that is recorded by the host and again given to the participants. So that is a path, right? So if there is a path, that is a network, we can communicate in a network if and only if the network is connected. Connected means here. Connected means if there is a path between the speaker and participants. What is the path? The speaker, the lecture given to the speaker will be posted by the host, and then the participants able to listen to the lecture. So this we call as connected. A graph consists of only one vertex is always connected because it doesn't contain any pair of vertices. So this example here the graph is connected. So take any two vertices, take two vertices, there is a path. Take these two vertices, there is a path between these two. Take this vertex and this vertex, this is one path, or you can combine this path. So therefore, or you can take this as a path. So take any two vertices of this graph, they are connected. There is a path. There is a path between two vertices. Therefore, this is connected graph. Suppose if I take this graph, it is not connected. Suppose if I take this vertex C and vertex A, these two vertices, there is no path. The path is only from C to B. From B to A, there is no edge. Similarly, from C to B, there is an edge, but B to A, there is no edge. Therefore, C and A, there is no path from C to A. Therefore, this is not connected. This is an example for not connected graph. This is an example for not connected graph. This one is example for connected graph. So the connectedness of the graph, example for the connectedness of the graph is this. You might be knowing a popular example in graph theory, the 7 bits of Unsimpel, Königsberg. The 7 bits of Königsberg. So this is the Königsberg city. The details are given here. Königsberg is a city on the Baltic Sea, located between Poland and Lithuania. A river runs through the city, which contains a small island. So this is the river, which is shown in blue color. This river runs through the city and contains a small island. The small island is here. So there are 7 bridges. So the bridges are denoted by green color. There are 7 bridges which connect the various land masses of the city. So different parts of the city are connected by 1, 2, 3, 4, 5, 6, 7 bridges. So this total thing can be represented like this. So this total thing is represented in a simple way like this, without showing that geographical map of the city. Just I would represent this in this form, right? So there are 7, 1, 2, 3, 4, 5, 6, 7 bridges. 7 bridges are shown here. Now, the people of Königsberg made a sport during 18th century of trying to cross each and every one of the 7 bridges exactly. Start from some bridge. Take this example. Start from some bridge, and then game is they have to cross each and every bridge exactly once and come to the same point. That's the game in the 18th century. The people of Königsberg sport during 18th century of trying to cross each and every one of 7 bridges exactly once. This way to be done in such a way that he would always end up at the very beginning. Suppose if he begins from this spot, he has to cross this spot. He has to cross all these 1, 2, 3, 4, 5, 6, 7 bridges. Again, he has to come here. Again, he has to come to this point. So therefore, the game is crossing all the 7 bridges one and only one time and reaching the same point. This is a game during the 18th century. So in 1736, Leonard Euler proved that it is not possible. Euler proved that this is not possible based on some theory related to graphs. Based on some graph theory, Euler proved that this is not possible. It is not possible to cross all the 7 bridges exactly once and come to the starting point. That is not possible. That was proved by Euler in 1736. So for that, there are some definitions. So Euler circuit, whatever the sport given here, that is called as Euler circuit. That is, Euler circuit is a path with a graph that covers each and every edge exactly once. Here, edges are nothing but the bridges. In this example, edges are nothing but bridges. Each and every edge exactly once and returns to the starting point. The game again start from the first point and cross each and every exactly once and come back to the same starting point. So that we call it as Euler circuit. Right? If a graph contains Euler circuit, then we call it as Euler graph. So a character graph has an Euler circuit if and only if each vertex has even degree. All these things are critical part corresponding to graph theory. I'm not giving the details, just I'm giving the important things which are required for this problem. Okay. So the connected graph has an Euler circuit if and only if vertex has an even degree. So if every vertex in the graph has even degree, then we can say that the graph has Euler circuit. If it is Euler circuit, then you can visit each and every edge exactly once. So coming to the problem, 7 bits of Königsberg. The Königsberg bits problem translated into graph, just I have shown the previous case. So this is a Königsberg problem. So here each island, we put one vertex for each island. So basically 1, 2, 3, 4 islands. So we're given 4 vertices. So therefore, by replacing each landmass with a dot, so this is one landmass, one dot, and the landmass under dot. Like this, each landmass denoted by a dot called a vertex or node, and each bridge. So what will be this is one bridge. So this bridge is denoted by edge. So this bridge is denoted by edge. This bridge is denoted by an edge, and this bridge is denoted by an edge, and this bridge is denoted by an edge. This bridge is denoted by an edge. So therefore, each landmass is denoted by a vertex. Sorry, dot. We call it as vertex or node, and each bridge is denoted by a line that we call it as edge or niche. Now, this problem is converted into a graph problem. So now this Königsberg bridge problem is converted to this type of graph problem. So this is complete now graph problem. Now observe this, as I told in the previous slide, if every vertex has the first statement, a connected graph has Euler circuit if and only every vertex has even degree. Now when you convert this into graph, now we have 1, 2, 3, 4 vertices A, B, C, D, where A, B, C, D are the landmasses. So what is the degree of this vertex? Degree of this vertex is 3. Degree of this vertex is 3. Degree of this vertex is 3. And degree of this vertex is 1, 2, 3, 4, 5. Degree of this vertex is 5. That means all the vertices have odd degree. In that graph, 3 nodes have degree 3. So this is degree 3, this is degree 3, this is degree 3, and one vertex has degree 5. That means all the vertices have degree odd. Since all the vertices have degree odd, so Euler circuit is not possible as per this last statement. So if every vertex has even degree, then there is a possibility of Euler circuit because all the vertices have odd degree. There is no Euler circuit. Therefore, whatever the sport was given in the 18th century is not possible. So this was proved by Euler by using graph theory. Planar graphs, all the graphs which are drawn in a plane. So we call it as K1. So this is a planar graph. So earlier, what is K4? You know what is K4? K4 means complete graph. Complete graph with fiber. This is K4. Suppose if you are able to redraw these edges such that no two edges intersect each other, if you are able to redraw these edges such that no two edges intersect each other, then we call that as planar graph. So here, earlier this edge was like this. This is replaced and we have drawn this edge because it is intersecting with this. We have replaced this edge by like this. This edge is connecting this vertex and this vertex. Instead of drawing this within this loop, I have written this outside this loop so that this edge will not intersect this edge. So if you are able to draw or redraw the graph such that the edges do not intersect, then we call it as planar graph. So this is another example for planar graph, K5. Is it planar or not? This is not planar because so this edge is intersecting with this edge, or this edge is intersecting with this edge, or so this edge is intersecting with this edge. Therefore, this is not planar. So K4 is planar, but K5 is not planar because it is not. K5 means what is K5? This is K5 complete graph where each vertex is connected. Right? Each vertex has only one edge. Every pair of vertex has only one edge. So this is that's incorrect. So therefore, this you are unable to redraw this such that they not intersect. So therefore, So applications of these planar graphs are realize a routine from the constructing a house, the water pipes. You have to arrange the water pipes such that no two water pipes go over the other, intersect each other. Even if intersect with some joint and other things, so they will not intersect like this. So you try to do the plumbing work such that the plumbers will do the plumbing work such that no two pipelines intersect each other. They're able to put the pipeline such that no two lines intersect. Similarly, the most obvious example are printed circuit boards and microchips. In microchips also, you see all the circuits. You can see the circuits which will not intersect, which will not go from all the others. So these are the applications of the planar graphs. The simple and important application is three-cottage problem. The problem is very simple and standard problem. Three-cottage problem is a well-known mathematical puzzle. It can be stated like this. It is well-known mathematical puzzle. Suppose that there are three cottages on a plane or a sphere on the earth, and each needs to be connected to the gas, water, and electric components. Is there a way to do so without any of the lines crossing each other? So these are the three cottages, and you have to provide three facilities: pipe, current, and gas. So water, gas, and electric. So these three cottages, these three facilities are to be provided such that one facility should not intersect the other facility. Is there any way to do so without any of the lines? Suppose if you provide a facility from this to here, and if you provide a facility from this water facility from this to second cottage, and this facility from this to third cottage. So similarly, on fire facility from this to first cottage, and this fire facility should not intersect with the water facility. Fire facility from this to second cottage, fire facility from this to third cottage, electric facility from this to second cottage, such that it should not intersect the fire facility and also water facility. And electric facility from this to first cottage, such that it should not intersect either water facility or fire facility. So these are the conditions. Now, is there any possibility to provide the facilities such that the line should not intersect each other? So this is nothing but example for a bipartite graph. Houses are taken as one set of things, and these are taken as another set of things. Then there are three houses and three facilities. You can represent this by K33. K33 is 3 by 3 bipartite graph. Now you have to draw this K33 bipartite graph such that no two lines intersect each other. So that is not possible. In more formal theoretical terms, the problem asks whether a complete bipartite graph K33, whatever I told in the previous case, is planar or not. So we proved in the 1930 that K33 is not planar. Thus, the three cottage problem has no solution. That is not possible to draw lines such that they do not intersect each other. Suppose H1, H2, the parties are denoted by H1, H2, H3, and unit is 5, water 5, and electricity we denote it by U1, U2, and the parties are denoted by H1, H2, H3. Now you can provide this water service from U1 to H1, and from H1 you can provide the gas service, fire service, and you can also provide electricity service from U3 to H1. Next, from H2 to U3, that is electricity service can be provided to the second cottage, and you can provide the water service to second cottage by this way, not like this, because if you provide like this, then this line will intersect. So that's why you can provide the water service to the second cottage, so like this. Then you can provide the electric service to third cottage directly, but you can provide the water services to the third cottage like this, so that it will not intersect. Similarly, you can provide the gas services to the third cottage like this. What is that? Whether all are covered or not? So what is this? Fire service to the second cottage is not covered. The fire service to the second cottage is not covered. So you cannot provide the fire service to the second cottage such that this line without intersecting this line with others. If you give like this, it is intersecting. Suppose if I give like this, it is intersecting. If I give like this, it is intersecting. Therefore, it is not possible to connect H to U. That is, you can provide water fire service to a second cottage without intersecting. So this is what. Suppose if I intersect this here, it is intersecting. If I provide by this line, then it is intersecting here. And if I provide this line, then it is intersecting here. Therefore, you are proving that K33 is not planar. You cannot draw the graph K33 such that no two edges intersect. So this is a standard example for proving K33, that is complete bipartite. K33 is not planar. Okay. This is another example, standard example for the graph theory. Then Hamiltonian cycles and plots, instead of each edge exactly once, here we take each vertex exactly once. So here, no less than sufficient, there is no less than sufficient condition for Hamiltonian, like in the previous violation of the degree of each vertex should be even. Then we say that side of either circuit exists and we can find other path. But here there is no such rule for less than sufficient condition. So here there is a Hamiltonian path, but no Hamiltonian cycle. Each vertex exactly one. So this is a Hamiltonian path. Hamiltonian path. This is a Hamiltonian. Each vertex exactly once. So this is a Hamiltonian path. Starting from here, B, C, F, E, D, G, H. So each vertex exactly once. Therefore, it has a Hamiltonian path. Hamiltonian cycle moves again from I and A, both should say. So that is not possible. Therefore, there is no Hamiltonian cycle, but there is an Hamiltonian path. If a graph has n vertices, then its Hamiltonian path must contain n minus 1 edges. By using this rules, trial and error method, you can construct the Hamiltonian cycle or Hamiltonian path for a given graph. As I told at the beginning, you can use Hamiltonian path or Hamiltonian cycle for tournament rankings. You can use Hamiltonian cycle or Hamiltonian path for tournament rankings. Suppose that n players compete in a round robin tournament, which I told at the beginning, only 3 players, here is 3 players. For every pair of players, you want to be either U beats B or B beats B. Either U defeats B or B defeats B. You can take any pair of players. Interpreting the results of round robin tournament can be a problematic. So we represent that in the form of graph, and we try to find Hamiltonian cycle to find the ranking, tournament ranking. That is who is the highest player. Who is the highest player? We give some ranking to the players by using this Hamiltonian cycle. So there might be all sorts of cycles where X beats Y, Y beats Z, Z beats X, like that. You can have several types of cycles, right? So graph theory provides at least a partial solution to this problem. So the result of round robin tournament can be represented with a tournament graph, which I have given in the beginning. Once again, I showed you. So this is a director graph in which the vertices represent the players and the edges indicate the outcomes of the games. Hence, if U defeats B, we draw an edge from U to B. In particular, an edge from U to B indicates that the player U defeated player B. That is an edge U to B. In a round robin tournament, every pair of players has a match. Thus, the tournament graph, there is either an edge from U to B or an edge from U to B. Or if you take any pair in a tournament graph, either there can be an edge from U to B or B to U. So this example, there are 1, 2, 3, 4, 5 pairs. So A, there is an edge from A to B. So edge from B to means U indicates that U defeated. So A defeated B. Therefore, an edge from A to B. And here C defeated B. Therefore, an edge from C to B. D defeated C. There is an edge from C to D. D defeated E. So edge from D to E. E defeated C. E to C. Like this, we have drawn a graph. This we call as tournament graph. Now we try to give some ranking. By using this, we try to give some ranking that we call as tournament ranking. In every round robin tournament, there exists a ranking of the players such that each player lost to the player ranked 1 position higher. Suppose if A defeats B, then we see that A has higher rank than B. If B defeats C, then B has higher rank than C. So like this, we give some ranking. So that we call it as tournament ranking. For example, the ranking is A defeats B. You take A, B, C, D. So A defeats B, therefore A is greater than B, and B defeats E, so B is greater than E. So E defeats C, therefore E is greater than C. C defeats A, so C is greater than A. So this is the tournament ranking. So this is what we have done in the next slide. So that from the next slide. Sum ranking. So A defeats B, B defeats D, D defeats E, E defeats E. So for all the 5 players, we have given sum ranking. So this can be done by using Hamiltonian circuits. This we can do it by Hamiltonian circuits. That is B lost to A, B lost to A. That is A defeats B, and then D lost to B, and E lost to D, and C lost to D. So that's why you got this graph. So in the graph terms, providing the existence of such ranking amounts to providing every tournament graph has Hamiltonian graph. If you draw a tournament graph, then every tournament graph has a Hamiltonian graph. That means you should be able to draw a Hamiltonian graph for any tournament graph. That Hamiltonian graph is nothing but tournament ranking. So this proof is by again every tournament graph has Hamiltonian graph. You can do this by using mathematical prediction. I am not giving the details of this. So this is application of the Hamiltonian. So application of the ideal graph is Conic square matrix problem. Application of this Hamiltonian graph is tournament ranking. Application of bipartite graphs is stable marriage problem or false marriage problem. So I have given 4 examples, and application of Hamiltonian cycles. This is a standard problem. I am skipping this. Then graph coloring. This is important. I'll give one example of an application of this graph coloring. With that, I shall try to close this. Graph coloring, you know what is graph coloring? Graph coloring is assigning colors to the vertices such that no 2 adjacent vertices have the same color. If you take some vertices of the graph, assign some colors to all these vertices such that these 2 should not have the same color, these 2 should not have the same color, and these 2 should not have the same color if they are connected. If they are connected, they should have the same color. That we call it as graph coloring. That we got as graph coloring. The minimum number of colors required to paint a graph, that we call it as chromatic number and denoted by xi of g. Suppose if I take this graph A, B, C, D, E. So A you can give one color because A is not connected to E. A is not connected to E. You can give another color to E, and E is not connected to C. You can use some more color to C. Suppose if I give a red color to A, then B, because B is connected to A, you cannot give the same red color. You have to use some other color, that is green color. And then because C is connected to B but not to A, therefore you can give the same color to C. The color you are given to A, that can be given to C. D. So D is connected to C, D is connected to B, D is connected to A. So it is connected to all the 3. So you cannot give the same 3 colors, you have to give a different color. So that's why the blue color is chosen here. And then D is connected to E, so you cannot give blue color here. And B is connected to C, you cannot give green color. And C is not connected to E, A is not connected to E. Therefore, you can give this red color to E. Therefore, E is red color. So therefore, how many colors are required? 3 colors are required. Therefore, chromatic number of this graph is 3. Chromatic number of this graph is. Suppose if we take any bipartite graph, its chromatic number is 2. So this is standard theorem in the graph theory. 4 color theorem is every planar graph is 4 colorable. So this is a 4 colorable theorem. So the planar graph is 4 colorable. That is 4 color. That is the vertices of every planar graph can be colored with at most 4 colors, so that no 2 adjacent receives the same color. Suppose if you want to color a region, if you are given a map, and if you want to color different regions of the map, then you can use this coloring graph with us. In that, what we do is we replace the regions of the map by vertices, and then we connect the regions if there is a boundary or border between 2 regions. Suppose if I take this one, so totally 1, 2, 3, 4 regions are there. 1, 2, 3, 4 regions. So for each region, we take a vertex. So in this region, we take one vertex. In this region, another vertex. In this region, another vertex. So take in this region, another vertex. So in each region, take 1 point. that we call divertex. And if there is a border, see, there is a border between this region and this region, so draw an edge. There is a border between these two regions, draw an edge between these two. There is a border between these two regions, so draw an edge between these two vertices. So there is an edge border between these two regions, so therefore draw an edge. So like this, you draw the graph. Therefore, the corresponding graph will be this. Now here to color this graph, just choose the colors of the vertices and use coloring of graphs. Once you color the vertices, choose this vertex color to total region so that the region can be colored. Another example is this, where say here there is a region here border between these two. Therefore, we have drawn an edge from these two. So there is a border from these two and it's from these two like this. This is same thing here also. The most important application of this is graph coloring is preparation of the examination schedule. Preparation of the examination schedule is the example or application of this graph coloring. Preparation of examination schedule. Suppose we want to schedule for final examination computer science course with the following subject course. So these are subject course. Subject course, you know, 1, 2, 3, 4, 5, 6, and 8. 3 plus 3, 8 subjects are there. Then for these subjects, you have to prepare the examination schedule such that there are some conditions. Suppose that there are no common students in the following pairs of courses because of prerequisites. So 1007 this subject code and 1007 and 3037 there are no common students. There are no common students for these two subjects. Similarly, there are no common students for these two subjects and these two subjects. But whereas, okay, like this, the lists are here. There are no common students from 1007 subject and the 203 subject. And there are no common students for this 1007 subject, 3261 subject, 3137 subject, 3261 subjects, 3203 subject, 3231 subjects. So in this, for these two subjects, there are no common students. For these two subjects, there are no common students. Like that, the conditions are given. So based on these conditions, how many slots are there? Totally 1, 2, 3, 4, 5, 6, 7, 8 subjects are there, such that there are some common students. No common students, there are some common students between two subjects. If you take the first one, last one, 1007 and 4, 1, 320330, 1, 2, 3, 4, 5, 6, 7. Okay. Suppose if I take 3137 subject, for 3137 to 3157 common, 3203, there are common students between these two. 3137 and 3203, there are some common students. Therefore, you have to prepare the examination schedule such that the number of days are minimum and there should not be any clash in the examinations. There should not be any clash in the examinations, and then the number of slots should be more. Even though there are 8 subjects, you should try to complete the examinations less than 8, maybe 3 or 4 slots or 3 or 4 days, so that there will not be any clash for the students writing the examination. One way is we put each exam on separate day, put on each exam on separate day. So there are 8 subjects. Therefore, examination can be conducted in 8 days. But the thing is, if you want to minimize the number of days based on these conditions, if you want to minimize the number of days, then you can use the coloring of the graphs. Right? So what we do is we convert this into graph coloring problem. So vertices are the vertices of the courses and edges of the courses that cannot be scheduled simultaneously because of possible students in count. Vertices are courses and edges are courses that cannot be scheduled. Suppose take these, all these are the vertices. I'll take all the courses for the vertices and then we draw some vertices. So put the edges where the students which were excluded, because 1007 to 3203 there are common students. Therefore, we are putting one edge from this subject to this subject. There are common students, putting one edge. So 1, 2, 3, 4, 5, 6, 7. So for this subject, for all the remaining subjects, with this subject there are common students. So 1007, 3203, there is common students. We put an edge. These two subjects, there is a common student, put an edge. These two subjects, there is a common student, put an edge here. These two subjects, there is a common student, put an edge. These two subjects, there is a common student, put an edge. These two subjects, there is a common student, put an edge. So if there is a common, if the students are common, Not common, not common. Students are not common. No common students. If students are not common, then put an edge. If students are not common, then put an edge like this. Then we try to the complement of this graph. Complement means so in the given graph, there is no edge between these two. There is no edge between these two. Therefore, we complement, we draw the edge between these two. Similarly, between these two, there is between these two, there is edge, between these two, there is an 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 edge. Like this, we try to draw the edges. Okay. This we call the lines in red color is a complementary graph. So we are taking these lines in blue color are the given conditions. So lines in red color are the complementary graph. That again I am retrying it again. Again, the retrying it complementary graph. Now what we do is just we are arranging. So now if you take one edge, these two cannot be given the same color. Now we transform it into like a graph color problem. If we cannot use only one color for all these, we cannot use only one color for all because these two are connected. This and this are connected, so these two should be given different colors. Therefore, the graph is not uncolorable. And similarly, there is a triangle. There is a triangle which is subset to this graph. With a triangle, this is a triangle which is subset to this graph. Therefore, it cannot be two colorable. Every triangle is two colorable. Every triangle is not two colorable. Take a triangle, you have to use 1, 2, 3 different colors. You cannot use two colors. More than two colors you have to use for every triangle. So because this has a triangle as a subgraph, the graph is not two color. You cannot use two colors. You have to use more than two colors. You cannot use one color for graph to color all the vertices. You cannot use two colors to color all the vertices. Now we'll try with 3 colors. We'll try with 3 colors. That is red, green, and blue. So first I will put this both are connected. Since this and this are both are connected, so 3203 red color and 3157. 3157 is yellow color, not blue color. 3203, 3157, and 4148 because 3203 is connected to this different color. This is connected to this different color. This is also connected to this different color because we are taking 3 again this triangle. We are taking this triangle. For this triangle, we are assigning 3 different colors. We are assigning 3 different colors to this triangle. 3 different colors to 3 edges of this triangle. No, so same thing. We have assigned 3 different colors to this triangle. Now you see, these two are not adjacent because there is no edge between these two. There is no edge between these two, and these two are adjacent. Because these two are adjacent, you cannot use this color here. Because these two are adjacent, you cannot use this green color here. Therefore, it will be yellow. You can use yellow color. So I am using this one, yellow color. And then, since these two are not 3261, these two are not adjacent, you can use the same color. And similarly, these two are not adjacent, you can use the same color, that is red color. Because there is no edge here, you can use the red color. There is no edge between these two, therefore, you can use the same red color here. So I have used 3 red colors, 2 green colors. And again, these two are adjacent to this 4118. These two are not adjacent, so 4118, therefore use green color. So otherwise, you can use this yellow color. You can use yellow color. Now, all the edges are colored. 3 with the green color, so 3 with red color, 4 with yellow color, and 1 with green color. So therefore, how many slots are required? So all these 3 in one slot, all these subjects can be in one slot, and this only one slot can be other slot, and all the remaining 3 can be under slot. That means totally 3 slots are required to conduct examinations for 8 subjects. 3 slots are required to conduct examinations for 8 subjects without any clash. So this is the application of the vertex coloring for preparing the examination schedule. For preparing the examination schedule, depending on some conditions. That means the conditions are there should not be any clash for the students writing the examinations. Okay. So these are a few applications of the graph theory. for the first case, bipocket graphs, I gave two applications on the stable knowledge or false knowledge problem. Parallel circuit, mixed word problem, or Hamiltonian circuit, tournament problem, and for planar graphs, three-cottage problem, and for graph coloring, examination sheeting problem. These are only few applications for the graph sheet like this. As I've shown in the beginning, third slide and fourth slide, there are many applications of the graph theory. Graphs can be drawn for many real-time problems, but we can apply the concepts of graphs to solve certain problems related to real life. So with this, I complete my lecture. Thank you. And I thank the organizers for giving me this opportunity to give a lecture on Thank you. Thank you.
Excuse me, sir.
Yes.
There are some queries from participants, sir. Mr. Nageshwar is asking about, please explain about isomorphism and homomorphisms.
My concentration is to take some simple concepts and the application related to the concept. So I'm not planned for explaining the graphs concepts of the graph theory. So what I prepared is I took some concept of the graph theory and what is the related application that I have explained. For example, if I take that islets into the Hamiltonian path. So Hamiltonian path, what is Hamiltonian path? How you can find it? Then what is the application of the Hamiltonian path? That is tournament ranking. Similarly, planar graph. What is a planar graph? How to draw the planar graph? What is the application of that? There is three-cottage problem. Right? I take some few concept and application related to that concept. I have not concentrated on the detailed concepts of the graph theory.
Okay, sir. Okay, sir. So please give real life applications of graph color, sir.
That's graph color. Just now I gave. No?
Yes, sir.
Even if you want to
Yes,
draw
sir.
a map and if you want
Yes.
to put different colors to a map,
Yes,
right?
sir.
A map contains different parts like draw a map or a person map or a city map or something else. Suppose if you want to map different cities in a state or different villages in a map in a district, then you can apply this color graph coloring to that. Suppose if you want to color different cities of a district with different colors such that no two adjacent cities have the same color. In that case, you can apply this graph coloring.
Okay, sir. That's all, sir. Okay, sir.
No doubts. Once again, I thank you
Okay,
for
sir.
giving me this opportunity. Thank you.
Thank you, sir. Thanks for the nice session, sir. And you explained the applications of graph 3D in other piece like communication, circuits, mechanical and hydraulic, financial and transportation with graph models very well, sir. And you explained about the how bipartite graph is used in Hall's marriage is very informative, sir. And after listening your session, we are learned about learned a lot, sir, and we now confidently explain the graph theory with the live examples, sir. Thank you, sir.
Okay. Okay. Thank you. Bye.
And and this is the time for vote of thanks, sir. On behalf of Gates Institute of Technology and Department of Humanities and Basic Sciences, today I take the opportunity to put all my gratitude in the form of words. First of all, I would like to thank our today's eminent speaker, D.Srinivasacharya, sir, for accepting our request and for giving such an amazing, wonderful presentation on graph theory and applications. Today's session is really fruitful and informative. Sir, you made this event really meaningful and interesting. Thank you very much, sir. We are very glad to have you today, sir. Thank you so much, sir.
Okay. Thank you. Thank you to all.
Thank you.
Thanks, participants, for listening carefully and patiently. Thank you.
Sir. Thank you, sir.
Bye.